Let me commence introducing once again this optoelectronic devices. So, optoelectronic device, they are special category of electronic devices. If on this pen. Okay, so they are the special category in the electronic devices. Okay, so it's one of the branch of engineering which deals with numerous optoelectronic devices. And these two pictures last class I told about you, this is basically an interaction of photons with semiconductor, an n type semiconductor, and adjacent to this you are seeing in another semiconductor which is a p type semiconductor. You are seeing on both the sides interaction of photons with n type and p type semiconductor, and here we have taken diffusion, density, doping concentration of donor ion concentration N d as 10 to the power of 15 per centimeter cube. Let us not worry about this number for the time being. You need to understand the what exactly photons does when they interact with the semiconductor. With reference to p type, let us say that we are choosing acceptor ion concentration as 10 to the power of 15 per cubic centimeter, and what exactly these photons create when they interact with the semiconductor. Okay, do you have any idea about this? What happens actually in the semiconductor when the photons are made to fall on the entire p type, n type or p type semiconductor? Okay. Basically, this is going to happen. So, the electron hole pair is going to happen. You have studied this concept in the module 1, right? Electron hole pair. What do we mean by electron hole pair? What do we mean by electron hole pair? We have studied this with reference to different bands.
Yes, recombination of electron and holes.
Recombination is opposite of electron hole pairing. Recombination is when electron comes back and recombine with the holes, that is recombination. Here what happens. So, this is going to be, suppose if I say this is going to be conduction band, this is a valence band. Electron acquires energy, in this case photons, they are the source of energy. When photons interact and you apply the energy, what is the amount of here energy required, which is equal to band gap, right. So, this is a band gap, let me call this as E g band gap. If you apply now, supply the photons, okay, which is greater than E g. Okay. Let us indicate this photons energy as h into mu. Okay. Suppose if I apply energy h into mu, which is greater than E g, what is going to happen now? Obviously, valence band is got the filled electrons, right. This is this region what you are seeing in the valence band. Let me show with electrons. So, these are all in semiconductor, the valence band is filled with electrons like this. So, now because of energy you are supplied, the electrons get energy from the photons and they get excited and they move into the conduction band. Let me show that conduction band. You can see that now conduction band is now the electrons have moved here and it creates an empty position here. Let me indicate empty positions like this, okay, because the electrons already left its position to the conduction band, and let me show the electrons here. So, you can see here the electrons now they are here. So, electrons have moved from valence band to the conduction band here. This is called electron hole pair. For every electron whatever you see here, there is a corresponding hole here. So, this process repeats, this is called electron hole pair. Okay. Now, here you see that earlier we have discussed the some potential we are going to apply to excite electron from the conduction valence band to the conduction band, but now the photons they are the source of energy, and energy must apply supply the photons such that it must be greater than the band gap energy here. Then electrons get excited and they move into the conduction band, and it helps in formation of electron hole pair. So, that means if you increase the number of photons here, okay, that means more number of photons are injected, okay, are made to fall on the n type or p type semiconductor. So, more number of electron hole pairs are created. So, that means electron hole pairing process keeps increasing when the number of photons keeps increase. Okay, it happens even in p type semiconductor. Okay, but this does not result in any current. So, this real application of the electron hole pairing and its movement that you see when you apply this inject impact this photons onto the p-n junction. Alone if you inject the photons to the n type semiconductor or p type semiconductor, it may increase the electrons and holes in equal number, but it does not give any significant or substantial amount of current here. So, therefore, alone having n type semiconductor and a photon interaction with that, it may create electron hole pair, but to create as a useful device, you must supply this the photonic energy to the p-n junction, that is nothing but diode. So, there you will see the real application of photon, okay, and the generation of EHP pair, and it results in a current in the p-n junction, may not be in n type and p type semiconductor. Okay, let us see the definition. Optoelectronics is one of the branch of engineering that deals with the interaction of photons. Photons we told already, it is a packet of energy, small packets of discrete amount of energy, or you can call that as electromagnetic radiation, that is called as a photon. They interact with the semiconductor and creates electron hole pair. More the photons, more electron hole pairs are created in the semiconductor. So, it is a basic unit of light and it is always in motion. So, photons will be always in motion and it will travel at the rate of 3 into 10 to the power of 8 meter per second. So, photons when they interact with semiconductor, the electronic devices basically they detect photons. So, the semiconductor devices when the that can be used, okay, optoelectronic device particularly that can be used to detect photons. So, optoelectronic devices can be used to emit photons. Optoelectronic devices can also be used to convert one form of energy to the another form of energy, particularly optical energy to electrical energy. In devices like solar cells and photodiodes, you can convert light energy into the electrical energy. That is possible using this optoelectronic devices. Okay. So, if you look at specific applications which detect photons are optical detectors, which are used in broadband telecommunication applications, and the optoelectronic devices which emit photons are light emitting diodes. They are the example for incoherent sources, and laser. Okay. What do you mean by laser? Any idea? You guys have any idea about laser? Have you seen laser in any application? Do you have an idea of laser?
Welding, sir.
Yeah, weldings. Why we use this lasers in welding? Do you have any importance of it? They are basically coherent sources.
I mean, sir, for the less time of interval, it will create a more energy, sir, as compared to the other sources.
Exactly. So, laser it stands for light amplification by stimulated emission of radiation. If you expand this, L stands for light amplification by stimulated, E stands for emission of radiation. Okay, so all this word if you expand L A S E R. Okay, so these kind of the sources. Okay, this lasers are basically highly directional. Okay, so this is highly directional. What do you mean by highly directional? Okay, highly directional.
It will not deviate.
It will not deviate. That's correct. It will be narrow beam. Okay, it will not direct. Next is it's going to be monochromatic. What do you mean by monochromatic?
Single wavelength.
Yeah, it's single wavelength, monochromatic. This is monochromatic. Coherent light, already we told about it. This is a coherent light. What do you mean by coherent source or coherent light?
When the two sources having the same frequency, it is known as coherent, sir.
Two sources.
When the two different sources have a common frequency, I mean frequency like a 20 hertz and for the one other frequency and the 20 hertz for the another frequency.
Yes, exactly. So, coherent means same frequency, we can say that. So, these are the different properties of the laser light. Okay. So, we will talk about this more when we come to the light emitting materials. Under that topic we will cover light emitting diodes and laser. But here to give brief information, laser is basically light amplification by stimulated emission of radiation, is highly directional beam, and it is monochromatic, and it is an example for coherent source. So, those the laser and the LEDs are typical applications which emit the photons. Okay. So, the last one, as I told you, solar cells are the best example. Solar cells, what they will do, which converts solar cells converts, or it converts absorbed optical energy into the useful electrical power. Okay. So, you might have seen solar panels on the rooftops. So, they convert basically an optical, it absorbs first of all the optical energy from the sunlight, and it is an example for renewable energy source. You might have seen that more and more solar energy, if you keep use it, it is advantage, you can replace with the conventional electrical system, because it uses solar energy and converts that into the optical electrical energy here. Okay. So, these are the typical applications of that. That means, generally the optoelectronic devices can be used to detect photons, to emit photons, and to convert one form of energy to other form of energy in a simplistic manner. Now, let us take photodiodes. Photodiode is a semiconductor device that converts light into electrical current, and the current is generated when the photons are absorbed in the photodiode. This is typically photodiode. Symbolic representation looks like this. If you have a diode, photodiode, you can show with the PN junction itself, but with arrow mark like this. Okay, if you show with arrow mark like this, it represents let me remove this. Okay. Okay, just you can indicate its symbol by showing two arrow marks like this. This shows that photons are injected, okay, are made to fall on the PN junction. The change in conductivity of these devices is proportional to the optical generation rate, and the photodiodes are the two terminal device designed to respond to the photon absorption. And there are two important properties of photodiodes. We will talk about this again, about properties. High sensitivity, this is one of the important property of a photodiode, and second thing is going to be the response speed. In fact, these two properties depends on various parameters of the photodiode. We will see that all those things in coming classes. Photodiodes, we will investigate the response of the PN junctions to the optical generation of electron hole pairs. The very important use of semiconductor junctions is solar cells. This is the typical introduction of the optoelectronic devices. Now, let us focus particularly little bit mathematics part of this optoelectronic devices. The topic is current and voltage in an illuminated junction. Okay. So, let us see generation current here. So, when we apply reverse bias to the PN junction, the current due to the drift of minority carriers across a junction is referred as generation current. So, normally we will call in reverse bias as reverse saturation current, or else you can give name as a generation current also. Thermally, these charge carriers keep moving, especially the minority carriers on n side, holes moving from n side to p side, and electron keep moving from p side to n side. These thermally generated carriers results in a current, therefore, this current is called as generation current. So, generation current flows from n to p, because this is due to the minority carriers. So, n means it is holes keep moving from n side to p side, therefore, generation current also flows from n side to p side. So, W is nothing but it is a space charge region or depletion region, what you are seeing. This is the energy band diagram of PN junction. As you are seeing here, this is under reverse bias. Reverse bias means we need to connect n region to the negative terminal of a battery and this p region to the positive terminal of a battery. Under this condition, you are seeing minority carrier movement from n to p holes and electrons from p to n. Now, let us see that electron carriers generated within the depletion region W are separated by the junction field. We know that within the W region here, there is a strong electric field. What is the direction of electric field? It is from n to p, you are seeing here. So, there is a strong electric field under reverse bias, which is acting from n to p. So, this is the electric field here. So, this what this electric field will do? So, electric field what it does is whenever this minority carriers comes close to the depletion region, they are swept into the p region. Okay. And whenever electrons comes near the depletion region, they are swept into the n region here. So, that is what it is told here. So, the strong electric field, that is electrons, the strong electric field causes the electrons to get collected in the n region, holes are collected in the p region. This is what the strong electric field in the depletion region does. The minority carriers generated thermally within the diffusion length of each side of the junction diffuse to the depletion region and are swept to the other side of the other side by the electric field. What do we mean by that? So, the minority carriers. So far you have seen that minority carriers which are close to the which are within the depletion region or close to the depletion region. Suppose if any charge carriers are within the diffusion length, here that suppose if this is the edge of a depletion region, suppose if I call this as my diffusion length. So, let me call this diffusion length as LP. What is LP? Any idea? What is LP? This we have discussed earlier classes. On P side, let me call as Ln. What do we mean by these parameters LP and Ln?
Concentration.
L stands for length, you remember? Diffusion length for holes.
Ln, yes, got it.
LP stands for diffusion length for holes and Ln stands for diffusion length for electrons. What do we mean by that? So, diffusion length of holes tells us how long the holes can travel in the n region before they get recombined with electrons. Similarly, Ln will tell you how much distance electron travels deeper in the p region before it get recombined with the holes. So, Ln is always taken in the p region, this is a p region. Okay, so, this is a p region and LP is always taken in n region and this is going to be the, it is measured from the edge of depletion region. Okay. LP is nothing but it is once again I repeat it, LP is the an average electron travels before it get recombined with the its hole, not electron. LP stands for diffusion length for hole. Average distance hole can travel before it recombine with the electron. Ln stands for average distance an electron can travel before it recombine with the holes in the p region. So, this Ln and LP is very important here. Now, if the light is made to fall on in this region, okay, let us see what is going to happen. So far we have seen that whenever the light is made to fall in this region, what is going to happen? There are three regions I am going to segment. One is depletion width, the second is neutral n region, third is neutral p region. We will analyze these three regions separately. Now, let us analyze the depletion region W. So, whenever photons are made to fall on this depletion width W, suppose if electrons and holes are there here, EHP electron hole pairs are there here. Now, this strong electric field here, we told that we need to operate diode under reverse bias only. So, strong electric field develops in the reverse bias. This electric field sweeps this electron from the depletion region to the n region. This is what you are seeing the arrow mark here. Okay. Similarly, the hole present here in the depletion region, these electron hole pairs are created because of the photons, okay, you have illuminated in the depletion region and because of that these electron hole pairs are created. Now, this electron keep moving to the n side because of the strong electric field in the depletion region. So, electron will be swept to the n region because of strong electric field in the depletion region and similarly the holes are swept into the p region because of the strong electric field in the depletion region. This is what it happens when the electron hole pairs are created due to the photons in the depletion region. Now, let us see and I think this part we can illustrate with one more diagram which I would like to show you better. You can see this. can see here, this is what type of junction this is? Anybody can guess? What kind of junction it is? Either Pn plus or Np plus. I am asking you what type of junction it is. Either this is a P plus N or Np plus junction.
Doping is more in the side of this
What kind of junction it is?
NP plus.
I think both are same. I must change here. I will change this. This must be N plus P. I must show this as N plus P. Now, tell me what kind of junction now this is. Is it P plus N or N plus P?
P plus N, sir.
P plus N, exactly correct. Because why this is P plus N? This is
Doping, I mean, most. The depletion region is less.
yes. The width you can see here. Depletion region is extended to which side? It is to the N side, right? So, therefore, whichever that is lightly doped, that side depletion region will extend. So, therefore, this junction is going to be a P plus N junction now. Understand this one? Okay. Now, let us move to the next diagram, which I will show you here. Observe here what happens now electron hole pairs when they are in the depletion region. Now, keep observing here when light is made to fall on this depletion region. Now, what happens here in this case? Okay. So, let us assume that photons are made to fall only on the depletion region now. Now, you can see that photons are interacting with the depletion region. This is the depletion region W. Okay. This is a W. Now, if electron hole pairs are created due to the photons on this, as we told that already strong electric field exists, you know the basic concept how this electric field is created. So, this strong electric field now pushes this hole to the P region, electron to the N region. It sweeps, it does not leave charge carriers because there is a strong electric field, strong capacitance here that pushes holes to the P region. So, holes are pushed like this, are swept like this. This electron is swept like this. This is what it happens, because of the strong electric field. Now, let us see the next diagram what it shows. Now, you can see here what is happening here because of okay. So, the strong electric field, you can see, observe here it is the holes they are getting drift to the P region, electrons are getting drift to the N region here. So, this is what it happens because depletion region will not hold any charge carriers. If by chance any electron hole pairs are created, this is what it happens in the depletion region because of the photons that create this electron hole pair, and the electric field will pushes holes to the P and electrons to the N side here. Okay. And next diagram you can see remaining two regions we are going to analyze in this diagram. Okay, so you can observe here. So far we have seen when the photons interact with in the depletion region, what is going to happen. In this diagram you are going to see when the photons are impacted in this region. Okay. So, let me show here when the photons are made to fall uniformly here, what is going to happen in this region. Okay. And same thing in this region also. Okay. So, this region you can see photons are, so this is little bigger arrow mark, I have increased the thickness here. Okay. So, this is photons injecting, interacting with the electrons. Okay. Now, I told you about 2 points right earlier. Okay. You can see here this is when the electron hole pairs are created in the depletion region, they are pushed, they are drift to the P region and N region. Now, see here we have to consider LP, that is what I was telling to you. LP is nothing but it is a diffusion length for holes in the N region. This is N type of semiconductor, this is P plus. So, now you can see that if at all any electron hole pairs are created in the neutral N region, now this get diffused because of the concentration gradient. holes will get diffused to the depletion region. Once the hole comes to this region, depletion region here, and accordingly the holes get drift into the P region by the strong electric field here. Okay. So, within this diffusion length, if electron hole pairs are created, so the holes get diffused because of the concentration gradient, they get diffused into the depletion region, and again the strong electric field here pushes holes into this region, into the P region. Same thing happens in the neutral P region, P plus region also. Suppose if the light, when we make to fall on the neutral P region here, this creates electron hole pair here. These are the electron hole pairs created due to the photons interaction with this semiconductor. So, these electron hole pairs, now you can see that it get diffused towards the junction. So, this when the H holes and electron get diffused towards the junction, now you can see that holes are pushed back into this region and electrons are pushed into this N region by the strong electric field here. Okay. I hope you understand three different segments here. One is with we explained with reference to different depletion region, what is going to happen to the electron hole pairs. So, it is a drift takes place and holes are pushed into the P plus region and electrons are pushed into the N region. We also discussed what happens when the electron hole pairs are created within the diffusion length LP on the N side, and we also discussed what happens when the electron hole pairs are created due to the photons within this Ln, and again see when they get diffused towards the junction, correspondingly the electrons are pushed into the N region, holes are pushed into the P region. That means, this region will collect electrons and this region will collect the holes because of the strong electric field here. Now, can you tell me the direction of current here, because due to the photons? We explained here drift mechanism and we explained the electron hole pair forming due to the photons here, and you are seeing now holes are collected by the P region, electrons are collected in the N region. Can you tell me the direction of current now in this due to the photons? Which direction the current is flowing, either from N to P plus or P plus to N region?
In the direction of holes.
In the direction of holes. So, direction of holes is nothing but it is from N to P plus. More of this is reverse bias. So, current flows like this. So, you can see that direction of field is also same as direction of current here. So, can we call this current as optical generation current IOP? Can we call this current as IOP? Because see, we have just applied reverse bias, that is all. Okay, we have connected this to the negative and we have connected this N region to the positive, that is all. Okay. Now, because these electron hole pairs are created not because of this power supply what you applied externally, it is due to the photons which are interacting. Due to that, these electron hole pairs are created. You can see three different segments here. In the depletion region, electron hole pairs created. In the P region, and electron hole pairs are created. These are all EHPs. You can see these are all EHPs, electron hole pairs. Okay, so this is an EHP and this is an EHP. So, these electron hole pairs are created because of the photons. Okay, these are all photons. Okay, and even here also. Okay, so photons are made to fall on the depletion region. So, now you can see that here all together leads for the holes to move from N to P plus region. Okay, so therefore, current flows from this current, let me call as optical generation current, it flows from N to P here now. Okay. So, now let us go back to the material. I hope you understand the mechanism of the hole movement and electron movement and the current direction in this optoelectronic device. Okay. Let me move back to the material. Okay. Now, we have seen we have discussed so far. So, you can see that when you apply this reverse bias, as you are seeing in this circuit diagram, we are applying reverse bias to this. We are not giving any potential here, just we are applying connecting with reverse bias, that is all. But within these regions, you have seen the electron hole pair forming, and that makes the holes to move from N to P. So, the current also flows from like this, from N to P. So, this is the direction of current in this. Okay, it flows from N to P. Now, let us see the segments here. different let me connect with mathematical aspects here. You have seen, we have understood what is this LP and GOP. Did we discuss GOP? GOP is called optical generation rate. It is a rate at which electron hole pairs are created. This GOP is nothing but generation rate, or let me call this one as optical generation rate. Okay. Now, if you multiply optical generation rate with A into LP, what is going to happen? What is this A into LP? You already know about LP. What is A? A is area of cross section or cross sectional area. Cross sectional area. When you multiply cross sectional area with the length, what it gives you? It gives you volume. Okay. A into LP corresponds to the volume. Now, when you multiply volume with the optical generation rate, what it gives you? Optical generation rate is nothing but it is the EHP generation rate only, the rate at which electron hole pairs are created. Maybe you can have some number like 20, 30, 100 millions like that. Okay. So, generation rate within this volume, okay, that tells us the extra volts that is generated on the N side, that gives us extra volts, because you are considering the N side. N side means we need to take up LP. Okay, this is nothing but diffusion length of the holes on the N region. So, these are the amount of extra volts generated on the N side. It depends on the optical generation rate. Okay. And similarly, you can also obtain the generation rate, electron generation rate on the P side, just multiplying this volume with optical generation rate. Okay. That gives us extra electrons generated on the P side. Okay. So, Ln corresponds to the P side, and A is nothing but area of cross section of the P region, P segment. And lastly, we have with reference to depletion region, A W into GOP. Again, A into W gives you the volume, okay, of the depletion region. Within that, the volume, the optical generation rate is GOP. So, these are the extra carriers generated within the depletion region. Now, all these three together results in a total current here. So, I already mentioned about optical current now under three segments. One is LP on N side, Ln on P side, and depletion region with W here, and that gets multiplied with this area. This you can also separate out this area into A into LP gives you the volume of in the N region. Okay. So, that is the cubical volume, and this is GOP is nothing but optical generation. This total current is nothing but Q times multiplied with this all this volume and the optical generation rate. So, this is the total current here. This is a mathematical equation for the optical current flowing in the PN junction. Okay. Now, let us see the total current, reverse current that flows in the PN junction. We need to consider even the forward current also. We need to now modify the diode equation we derived to incorporate the new optical generation current. We know that conventional current through the PN junction as this, right? I is equal to I naught. This is nothing but diode current. Diode current. And look at the second term here, this gets modified with this. Diode current remains as it is, but now from equation 1 we have subtracted this optical current here. Why we have subtracted optical current? Any idea? What is the necessity of subtracting optical current from diode current? Look at the direction. Which direction the diode current is flowing? This is diode current. It is from N to P, right? It is from P to N actually. This is from P to N. And what about optical current? It is from N to P. So, therefore, the directions are going to be totally opposite. Okay. So, with that is why you are seeing here negative sign. The basic diode current we have modified with this. This is the total current flowing in the PN junction due to the photons interaction. Okay. This is all we have told earlier. So, GOP this LP into this product area of cross section gives you the volume that should be multiplied with optical generation rate and Q to get the current equation. Okay. This is within end semiconductor also we have seen when the photons are interacted, it gives you the holes are generated at this rate. So, optical current in the P semi or N or P semiconductor is given by this. Okay. So, this is in N type semiconductor. So, because this we have taken here N block, okay, under this the optical current generated is very small amount of current that may result, because there is no strong electric field here. So, this is the current. Now, here one more equation which you need to aware, this is called reverse saturation current. In this equation we have here I naught. You can see that I naught corresponds to reverse saturation current. So, I naught is given by this mathematical equation. We have discussed this in previous chapter. This reverse saturation current or thermally generated current is given by Q times Ni square into A, that gets multiplied with dN by Ln into Na, and dP by dP stands for diffusion constant for holes, by Lp times Nd. This is total is I naught. Okay. That is subtracted with optical generation current, that gives you the total current. In fact, this is not ITH, this is going to be the total current I, okay, which is equal to the reverse saturation current into this factor minus this IOP. So, that is the equation 3 here. Okay. Any questions about so far? So, same thing we have rewritten here, all those things you can go through these equations. Okay. So, any questions about this so far? So, finally, we end up with this equation, optical generation current and total current here, total photodiode current as this equation. Okay. Do not worry about equation numbers, because written at different times, therefore, I given different equation numbers. So, this is the overall current flowing in the photodiode. Okay. So, due to the photons, you can look at this. So, this equation you need to remember this with all details we have given, instead of abbreviating with small things. Okay. Okay. Now, if you observe equation 3, this has got the two parts here, first part and the second part you can see here. The first part tells you the diode current, usual diode equation. The second part tells you the optical generation current. Okay. So, the same when this is with the pictorial representation we have shown here, how exactly the currents are generated. Let us look at characteristics now. If you look at voltage versus current characteristics, so if you observe here, which contains all total characteristics. This is the forward characteristics. When you keep PN junction under forward bias, this is the amount of current, exponential current flows here. But look at when you reverse bias it without any photons interaction. Okay, you are seeing here, if you do not allow this photons, okay, if you are not allowing this, then this characteristics is applicable. You can see that this is the characteristics comes into play. GOP 0, that means no photons. This current is also called as the current that is flowing here. This is GOP, means it is a optical generation rate. So, optical generation rate is going to be 0. That means there is this is a current here called as reverse saturation current. So, without photons, this GOP is equal to 0 means no photons. Photons are not made to fall on the PN junction without photons. So, without this light, what you are saying is the current flows, this I naught current flows from N to P. This is the I naught current. So, this current is also called as dark current. So, this is called as a dark current. There is no photons here, that is why it is called as a dark current. Okay. Now, as you keep increasing the photons here, you can see that generation rate keeps on increasing. So, G1 is less, G2 is increased compared to G1, G3 is further increased compared to G2 and G1. Okay. So, these are nothing but generation rates. As you can see here, G3 is greater compared to G2 compared to G1 here. Now, if you increase the photons now, okay, so now if you increase this photons, okay, Now, you can see that photons are made to fall on this. Now, because of the photons now interacting with this, you will get electron hole pairs in all three regions that creates uh, not I naught now. Now, the current will change, the magnitude of current will increase. Now, we can call this as IOP, optical current now. Now, you can see that we have different IOPs now here. Due to the generation rate G1, we have this distance will tell you the current here. Okay. This distance. More the distance, more current is flowing, you can see here. Since it is reverse biased, so you get more current here. Okay. So, G1, G2, G3. So, current keeps increasing here. Okay. And we will see that here, what happens when the voltage is 0 here. Do we get any current here? You can see here. These points, wherever I marked into here, those are the points in which we are going to make the photodiode a short circuit across that. Okay. When you short circuit, the voltage is going to be 0. These are the points where voltages are 0, voltage is 0. External voltage whatever you apply, if you make this as 0, okay, so this but your now current is flowing only due to the photons now, but there is a closed path here. Okay, so the current flows because of the only photons here. So that with that you can calculate what is the amount of current here. Okay. Okay, so that we will discuss here, as you can see here, but this I have a separate material for this. I will take up that and discuss about this short circuit, and here you need to consider open circuit, because these curves will not stop here. These curves will extend even to the first quadrant, you can see like this. Okay. All curves will interact like this. Okay. At this point, as we have seen, on y axis the voltage is 0, because voltage is 0, but on x axis you can see that current is 0. So, when voltage is 0, so that means you need to apply a short circuit. Is it correct? Short circuit? Yes. Short circuit, the voltage is going to be 0, and when you want to make current as 0, you just want to open circuit it. If you have a photodiode with you like this, you apply across this the short circuit like this and calculate current flow here, because now photons here. When you apply short circuit, so voltage is 0 here, current flows here. Let us call this as ISC. Okay. Now, when you make open circuit here, when you have a photodiode with us, okay, there is a open circuit now. Let us call this as VOC is equal to now applied voltage across these two terminals. Now, current is going to be 0 here, there is no current here, current is going to be 0 here, but you can calculate open circuit voltage VOC. Okay. So, two different aspects you need to discuss to understand these curves in the fourth quadrant. In third quadrant, there is nothing to say here, because in third quadrant we apply reverse bias, and as you increase the photons, number of photons, accordingly current keeps increasing. As we told already, G1 is a generation rate which some amount of current flows. For increased photons, generation rate increases and current also increases. As you can see here, current is negative, voltage is also negative because of reverse bias. Now, to further extend this into the fourth quadrant here, you need to find out here the extreme conditions, like the short circuit, where we need to make in our current equation the voltage as 0 and try to find out the current resulting. That current we call as a short circuit current, and when we make the current 0, we call that as a open circuit conditions. So, under these two conditions we can estimate the point here, because this region is very important for us. All our solar cells operate under fourth quadrant. So, this is the region of operation of solar cells. If anybody wants to do a project work or to understand basics of solar cells, you need to understand the fourth quadrant operation of photodiode. Okay. The photodiode can be used as a source of energy when you operate in the fourth quadrant. Okay. Here the real application of the photodiode, okay, is a solar cell. The photodiode can be used as a solar cell when we operate in the fourth quadrant here. We will see how this can be operated as a fourth quadrant, but you can see here in the third quadrant and in the first quadrant, this is like the photodiode need to be supplied with an energy, whereas here in the fourth quadrant the photodiode itself provides energy. Only thing is you need to apply the photons are get converted into the electrical energy. So, here we can use a photodiode as a solar cell, and that gives that can be used to source circuits, but here you have to provide the external energy to function the diode here. Okay, that is the difference. Any questions so far? Hope you understand this the characteristics much better. So, we will take up this in a separate derivations, there you will understand better. Okay. Any questions about this? You hope you understand this open circuit and short circuit conditions here. Why we need to do short circuit condition? To obtain the extreme ends of these curves. Okay. These points especially. To identify these points, you know that if you make voltage as 0, you are going to end on x axis on y axis here. So, to know these values here, you must short circuit the photodiode here. In order to determine this where exactly it crosses voltage axis, you must make current as 0. When you make current as 0, you end up on the x axis here. So, these two conditions you must analyze here. One is, as I already told you, open circuit condition and a short circuit condition. Short circuit condition means you need to find out short circuit voltage here. This is called current you need to find out. Under this short circuit condition, you must find what is ISC. Under open circuit condition, you must find what is VOC. This gives you VOC. So, these are the two things we need to identify here. So, this gives us ISC. Say for example, ISC 3, this gives you ISC 2, this gives you ISC 1. Similarly, here you will have three different points of the VOC, VOC 1, VOC 2, VOC 3. So, then you can extend these curves in the fourth quadrant here. This region of operation of fourth quadrant here, this region, okay, and this is the region of operation of solar cell. Okay. If you operate the photodiode in this fourth quadrant region, instead of taking the supply, it gives supply, it provides the source, it acts like a source. So, solar cells are nothing but they act like a source here. So, now this is what you need to understand from our basic optical current equation. This current equation what we have derived here, using this equation, now we need to obtain these two conditions, open circuit condition and short circuit condition here. Now, you can see here we short circuit the device. When you make V is equal to 0, what is going to happen here? This is called short circuit, you can see here, and there is a short circuit current flowing in this. You can see that when you make short circuit, if you consider this same equation, a total current equation. So, when you make short circuit, you can see that V is going to become 0. So, you can see that when you make V is equal to 0, the first term will get eliminate, because e to the power of 0 is nothing but 1, this cancels with each other and you are left out with only IOP. So, therefore, total current is now is equal to the minus of IOP. So, this is the current short circuit current flows in the photodiode. Okay. So, this is the current generally we have derived here. You can also obtain for each one of this here if you know the values of optical current values. Similarly, to obtain open circuit conditions, you need to apply open circuit here. Open circuit means you need to just open this across photodiode, and by opening this you need to calculate what is open circuit voltage here. To do that, what you can do is you can just make I as 0. When you make I as 0 in this equation, you can see this is the resulting equation, and if you simplify this, okay, you are going to get this equation VOC, approximately this equation you get it. In the next class, I will derive and show you how you get this equation. So, one is open circuit voltage equation we have, another is short circuit current we have here. Okay. So, these are the extreme region of operation of a solar cell. Understand here? If somebody asks you what is the maximum region where you can operate solar cell, the maximum region or power that you can extract from solar cell is VOC ISC. So, this is the amount of energy you can extract from the solar cell. I am sorry. Okay. So, this is the amount of energy we can extract from the solar cell. VOC, it is the maximum open circuit voltage, and current here. So, product of these two gives you the amount of energy that can be extracted from the solar cell. So, in the next class we will derive this mathematical equation for the VOC, and they will understand much better about open circuit voltage and short circuit current here. And finally, we have this energy band diagram of equilibrium condition and for the this photo diode. You can see here this is now Q into VOC, this is the amount of voltage you need to consider here, and FP is nothing but Fermi level on the P side and Fermi level on the N side. You can see Fermi level on N side is above and then the Fermi level on the P side. So, this gives you the energy levels of photodiode here. Okay. We will continue this class in the tomorrow, and we will discuss this equation and more about this energy band diagram here. So, at this point I will stop here, and if you have any questions I can take it offline.